chapter 6. We'll start off problem number 623. Okay. Assign the oxidation, redox oxidation numbers to the atoms in the following. All right. If it's a simple polyatomic ion like S2 minus, it's just the 2 minus. All right. So for A, it's 2 minus. We have a compound, SO2. We have to look at the rules. The rules are on page 217. Oxygen should have a -2 on it. That's a rule. Sulfur doesn't necessarily have a rule. So oxygen -2 with the 2 -2s, that's a -4. And then sulfur is going to have a +4 because the sum of all the oxidation numbers has to add up to whatever the charge is on the molecule or the polyatomic ion or compound. All right. So this compound here, this molecule, has no charge on it. There's no charge here. So sulfur has to have a +4. Each oxygen has a -2. C, P4, when you have something like that, P4, the sum of all the charges has to add up to 0. Therefore, there can't be any charge on that, on any of those atoms there, right? There's no oxidation state. Oxidation state is 0 for everything. So 0, right? For C, answer is 0. pH3. pH3, each H has to have a plus. That's a total of +3. Therefore, phosphorus has to have a -3. So each H has a plus, and each phosphorus has a -3. All right. 625. Assign the oxidation numbers for each of the following: NaOCl, sodium hypochlorite, right? So this is a compound, an ionic compound. This has a plus charge and that has a minus charge on it, right? So we can do two things here. We can split this up into ions, whoops, OCl minus, and we can solve them individually, or we can solve them together, because again, the sum is going to be, the sum of the oxidation numbers is going to be equal to the charge that's on the compound. So the sodium is going to have a +1, and in an ionic compound, the charge on the ions, if it's a monatomic ion, then the charge on that ion is the oxidation number as well. So sodium is a +1. This is the polyatomic ion here. Oxygen is a -2. Chlorine has to have a +1 so that the result is a -1 charge. Now, chlorine's rule generally is that it has a -1 charge, right? But oxygen's rule is a -2, and oxygen's rule supersedes that of chlorine. It's higher up on that list, right? It's rule number 5, whereas the chlorine rule pertains to chlorine is number 6. All right, so oxygen's -2, chlorine is +1 in that compound, and sodium is +1 as well. All right. So the sodium chlorate, NaClO3. All right, we have the same situation. The sodium has a plus charge. Oxygen has a -2. There's 3 of them, so that's a -6. So chlorine has to have a +6 so that this, it has to have a +5 so that this sum of this will be equal to 0, which is this charge on that ionic compound, right? We could have easily taken the ClO3 minus separate as well. And again, -2, -6, and it's going to have a +5, so we can have a minus charge there. All right, so sodium has a +1, chlorine has a +5, and oxygen has a -2. Sodium perchlorate, NaClO4 here. Sodium has a +1, oxygen has a -2. There's a 4, -8, so this has a +7. +1, +7, -2. All right, 627. Assign oxidation numbers to the elements in the following. All right, lead sulfide, PbS. All right, so this is a +2 and a -2. Just the charge on the ions when it's an ionic compound. All right, titanium chloride, TiCl4. Yeah. Just making sure there that we're retaining that right. Yeah, titanium chloride, that's right. Okay. Cl has a -1 and titanium has a +1. 4. Right? Again, ionic compound. Cesium oxide, ionic compound. Cesium has a +2. Oxygen has a, no, cesium has a, let's see, CSO2. CSO2. Cesium. CSO2. Well, I'm wondering if this is miswritten instead of, should be that, right? Cesium oxide. But if this compound is written the way it's supposed to be written, then -2, -4, that means the cesium has to have a +4 charge on it, which would be bizarre. We would expect the cesium to have a +1 charge and oxygen to have a -2 charge, right? So let's look that one in the back and see if we can find out anything about the answer. (627). Let's see, what are we on now? 6. Whoops, I forgot to change that up there. We're on 627. 627. Let's make sure. 627. C. Oh, no, my mistake. Let's see here. Let's see, so the compound is correct. Oh, yes, so the compound is correct, but cesium had its rule associated with, so this is the correct compound here. And the rule associated with cesium is above that of oxygen, above that for the oxygen. So this has to have a +1, and then this one has to have a -1/2. Okay? There's 2 of them, and that gives us a sum, no net charge on the compound. All right. Cesium oxide, oxygen fluoride, or dioxygen difluoride, O2F2. All right, this compound here, fluorine, always has a -1, so that's a -2. So oxygen, each one has to have a +1. So fluorine has a -1, and oxygen has a +1. Okay? Let me put a note here. 629. Okay, 629. Titanium burns in pure nitrogen to form TiN. What are the oxidation states of titanium and nitrogen in TiN? Well, titanium is not a group 1 or group 2 metal, right? So we can look at our rules there. Group 1A and 2 and aluminum all have +1 and +2 and +3 respectively. So titanium, no rule, so nitrogen has a -3, so titanium has to have a +3. All right, so the answer for 629, -3, +3, and -3. Good. So now, we knew this because basically it's an ionic compound and the charge is on the ions, right? Okay. 631. Ozone is one of the oxidants responsible for the haze over the Smoky Mountain. What's the oxidation number of the oxygen in ozone? O3. Well, it has to be 0, right? Because there's no charge on this compound, so each oxygen can't have an oxidation number. It has to be 0. Let's see, that was 631. 633. The chlorine is added to drinking water to kill bacteria. Some of the chlorine change into ions by the following equilibrium. In the forward reaction, the reaction going from left to right, which substance is oxidized and which substance is reduced? In the reverse reaction, which is the oxidizing agent and which is the reducing agent? So we can look at the chemical formula there on 633. chlorine gas, and it is being converted or interacting with water, and the products are proton, chloride ion, and let's see, that is hypochlorite. Hypochlorite goes to us, hypochlorous acid, HOCl, right? Okay, so we can look at the oxidation numbers for all the elements here. Oxidation number for chlorine is 0, oxygen -2, hydrogen +1. Hydrogen here is a +1, as the charge is the oxidation state for both of those. Hydrogen +1, oxygen -2, chlorine. So what is chlorine going to do? Well, chlorine has to be a +1 here so that this whole thing has a stable charge. And the question was, what was oxidized and what was reduced? Well, here on the left side, chlorines, both chlorines have no oxidation state, just a 0. If we go to the right, though, we see one with a -1 and one with a +1. Therefore, chlorine was oxidized and chlorine was reduced. So the question is, in the forward reaction, which substance is being oxidized and which is being reduced? The chlorine, both. One atom is being oxidized and one is being reduced. In the reverse reaction, which reaction is being oxidized and which is being reduced? In the reverse reaction, we have chlorine ion being oxidized, the chlorine gas here. Chlorine with a plus charge being reduced to it with Cl0 there. Okay. 633. When chlorine is at, oh, that was what we just did, sorry, 635. For the following reactions, identify the substance oxidized, the substance reduced, the oxidizing agent, and the reducing agent. Okay, so 2HNO3, H3ASO3. And O, two of them. 3H3ASO4. And water. We identify oxidation states for all of these compounds, or all the elements within the compounds. -2 plus 1, -6 because there's 3 of them there, +1, so this has to have a +5 on it. Nitrogen there has a +5. Here we go, +1. Oxygen -2, so there's a +3 because there's 3 of them here. There's a -6 because there's 3 of those. So arsenic here has to have a +3 on it. Oxygen -2, nitrogen +2. Oxygen, hydrogen +1. There's a +3 due to the 3 element there. Oxygen -2, -8, +5 there, -2 +1. Okay, so we have all the states now, and we see that nitrogen goes from a +5 to a +2. That's a reduction. The arsenic goes from a +3 to a +5. That's an oxidation. So this is being reduced. This is being oxidized. Specifically, the nitrogen is being reduced, oxidized. The arsenic's being oxidized. This is the reducing agent. It oxidized this compound. This is the oxidizing agent. It oxidized this compound over here. Okay? Next one, 635. B, sodium iodide. HOCl. NaIO3, sodium iodide, where are we at? 3HCl. Okay, so you have to identify the oxidation numbers there. All right, sodium plus, iodine minus, H plus, oxygen -2, chlorine has to have a plus charge there. Sodium plus, iodine or oxygen minus 2, minus 6, plus 5 on the iodine. Plus, minus. All right, so we see the Cl went from a plus to a minus. Iodine went from a minus to a plus 5. All right, minus to a plus 5. This is being oxidized. It's the reducing agent. Specifically, it was the iodine that was oxidized. This is being reduced. It was the oxidizing agent. All right, are we answering everything that we need to for these ones? Oxidizing agent and the reducing agent, yeah. KMNO4, 5H2C2O4. Oops, still on 635. Okay, so we have potassium permanganate, this is the carbonate, this is the carboxylate, carboxylic acid, carboxylate ion, sulfuric acid, which one is it, 635, this is, and then we have carbon dioxide, potassium sulfate, manganese sulfate. Manganese sulfate, and water. Okay, so we have, let's double check this here, 2 potassium permanganates, 5 this is a carboxylate, carboxylic acid, that's right. 3, I didn't get the 3 there. 3 sulfuric acids, 10 carbon dioxides, 1 potassium sulfate, 2 manganese sulfates. Not that these numbers change anything, right? The coefficients don't change what the oxidation numbers on the elements are, but just in case. All right, so we have, okay, we have to identify what's being oxidized, what's being reduced. So we look at the elements, right? Potassium here is in an ion, so we see, I mean, it's an ionic compound here and an ionic compound here, so we know that it's not going to be changing. The manganese here, however, is in a polyatomic ion here, and then it's in an ionic compound here, so it's probably manganese, right? Now, we can go through and check them all, but I'm trying to kind of save ourselves some time. Oxygen here, it might be changing there. Carbon, though, is for sure, well, I would bet the carbon's changing. The sulfate isn't changing. It's the sulfate here, the sulfate there. It's not changing oxidation state. So I'm going to look at the manganese here. Minus 2 for the oxygen, minus 8 altogether, plus 1 for the potassium. Now, manganese here has a plus 7, therefore, right? So that the minus 1 and the plus 7 will equal the minus 8, so that the overall charge will be equal to 0. All right, and the manganese here, minus 2 for that sulfate ion, so it's a plus 2 on that manganese. So there's manganese being reduced, right? Manganese is being reduced. That means this is being reduced, and that's the oxidizing agent as well. The carbon here, oxygen minus 2, there's 4 of them, minus 8. Hydrogen plus 1, there's 2 of them, plus 2. So we need a plus 6. Oh no, there's 2 of them, so plus 3. Plus 3 on each carbon, so there's a total of plus 6, so that these values add up to 0. Whereas here, the oxygen minus 2, minus 4, carbon is plus 4. So oxygen was, no, sorry, plus 3 to plus 4. Carbon plus 3 to plus 4 was oxidized. So this is the reducing agent. It was, did I say that right? This was oxidized, so it's the reducing agent. This was oxidized, so it's the reducing agent. All right, so we found it. Good. And you can go through and check all the rest, but you'll see that their oxidation states do not change. All right, 637. All right, balance the following equations for reactions occurring in acidic solutions. S2O3 2 minus plus OCl minus, yielding chloride ion. Oops. Cl minus, S4O6 2 minus. Okay? All right, so the first thing we do is we verify that the, well, what do we do? First thing we do, well, so this is the first time we balanced redox reactions, and you have to use your, let's see, where is it at? Acid as an oxidizing agent. You have to use your, what you call your ion electron method, okay? So to follow how to do the ion electron method, where is it at? Balancing redox reactions for basic solutions, balancing redox reactions, so balancing redox reactions, page 223, we start our methods, okay? And the first thing we want to do is we want to separate these into half reactions, okay? So, I don't know if I have much space on this board, but we'll do our best. We'll separate. One half reaction here is S2O3 2 minus going to S4O6 2 minus, all right? First thing we do is we balance everything except for oxygen and hydrogen. That means, in this case, sulfur. We need to have a 2 there, right? Because there's 4 here. Now we don't worry about the oxygens at that conjunction. Okay, I'm going to have to erase this and use a little more space here. Probably not going to have room to do both of them, both half reactions on the same board. Okay, so the next thing I need to do is balance oxygens by adding oxygen, or balance oxygen by adding water. So here I have 6 oxygens and 6 oxygens there. So that's balanced. I don't have to balance oxygens. And then I balance hydrogens by adding protons, but everything seems to be balanced. So all I have to do here now is adding balance charges by adding electrons to the more positive side. Well, this has a -2 charge over here. This has a -4 charge over here. So I have to add, and the -2 is the sum of all the charges. This is a -2, but there's 2 of them, so there's a sum of -4 charges on the left and a -2 on the right. So the more positive side is this side. This side's a -4, this side's only a -2. So this side is more positive. And we then add electrons to the more positive side, and that's 2 electrons there. So now that this has a -2, and then there's 2 more minuses, and this has a -4. So there's a -4 charge over here and a -4 charge over here. So we balance the charge by adding electrons to the more positive side. All right, now that half reaction is done, and so we'll go to the next half reaction, see if we can sneak it in here. Sneak it in here. The OCl minus going to Cl minus. First, balance everything that's not oxygen and hydrogen. Chlorines are balanced. Second, balance oxygens by adding water to the side that needs more oxygen. All right. Now we balance, so we need 1 water over here because we had 1 oxygen. Now we balance protons, or H's, by adding protons to the side that needs more. And we need 2 H pluses over here to balance the 2 H's over here. Okay? So now we add electrons to the more positive side. The charge over here, the sum of the charges over here is a +1, right? We have 2 pluses here and a 1 minus here. So it's a +1 here. The sum of the charge over here is -1. So we have +1. So we need 2 electrons added to this side, because that'll now give us a charge of -1 total over here. And over here on this side, the sum of the charge is -1. Now to finish the reaction here, we take the first half reaction, add it to the second one, 2S2O3 2 minus, add it to the second one, 2 electrons, 2 H pluses, and OCl minus, all right, hypochlorite ion. So I should say that before I could add these together, I had to verify that the number of electrons being added to the right side of the equation here and added to the left side of the equation here, that number of electrons had to be the same before I could add these 2 half reactions together. All right, so where were we at? 2 H pluses, 2 LC minus, arrow S4O6 2 minus, plus 2 electrons, plus down here now, Cl minus, plus H2O. All right. Now we can cross out anything that there's multiples of, and that looks like our electrons. The electrons should always be canceled out. You're never going to have electrons showing up in any chemical reaction, all right? They show up in half reactions, which aren't real chemical reactions. They're just portions of reactions that we can match up with other half reactions. But in the final reaction, you should have no electrons. All right, everything else looks like it has to be there. So let's double check this one. Oh, this was a 637A. 637A, OCO minus, 2 protons, 2 S2O3s, 2 minus, S4O6, 2 minus, chloride ion, and water. All right, good. 637B. NO3 minus, copper, NO2, copper 2 plus. All right, everything that's not, well, first we break it up into half reactions, NO3 minus and NO2. The other half reaction is copper going to copper plus 2, right? We balance everything that's not oxygen or hydrogen. The nitrogens are balanced. We balance oxygens by adding water to the side that needs the oxygens. We balance hydrogens by adding protons to the side that needs them, okay? And then we balance electrons by adding electrons to the more positive side. That's this side over here. We have a sum charge here of +1. So we have 1 electron being added here. All right, copper and copper ion here. Balance everything that's not oxygen and hydrogen. It's done. Balance the oxygens, done. Balance the protons with adding hydrogen ions, done. We just need to add 2 electrons to the more positive side. All right. After we do that, we're ready to combine, except that 2 electrons here and 1 electron in that half reaction. So we need to multiply everything up here by 2, 4, 2, 2, 2. And now we can combine, because now the electrons will cancel out. So the combined reaction, 4 protons plus 2 NO3s. Oh yeah, 4 electrons, 2 electrons. 4 protons, 2 NO3s. A copper now from here, arrow, 2 NO2s, 2 H2Os, 1 copper, 2 plus ion, and 2 electrons. The electrons cancel out on both sides. And that looks like it. 4 protons plus 2 NO3s plus copper ion, or metal, copper atom, yields 2 nitrogen dioxides, 2 waters, and a copper ion. Okay, I can double check that one, 637B. Okay, 637C. IO3, H3, ASO3. Iodine, H3, ASO4. Iodide ion. Okay, so now we have, again, break it down into its half reactions, IO3 and iodide. Here we balance everything that's not oxygen and hydrogen. It's done. Balance oxygens by putting water on the side that needs the oxygens. We need 3 oxygens. Now we add 6 H pluses over here. We add electrons to the more positive side. Let's try that again. 6 electrons. All right. So, that's that half of the reaction. H3ASO3 going to H3ASO4. The arsenics are balanced. We need 1 more oxygen over here, so we add a water over here to the left. Now we need to balance the protons. We have 3, 3, and 2 more. Let's verify that we have that written down right. Yeah. Okay, so we need 2 more protons over here. Two H pluses, sorry. Okay? Now we need to add electrons to the more positive side, which is right here. All right, so 2 electrons on the bottom, 6 electrons on the top. This one has to be multiplied by 3. 6. 6. Okay, now we can add everything together. I'm not going to write the electrons in because we have seen already that they always drop out. All right. And I also see that there's 6 H pluses here and 6 H pluses there, so I'm not going to write those in either. You can see that they're going to drop out. So we have IO3 plus, down here, 3 waters plus 3H3ASO3, yielding iodine. Wait, what was this? An I minus? Yeah, this has an I minus charge on it, right? Iodine plus 3 H2Os from up here. Oh, we had 3 waters, 2 on both sides. Well, 3 waters over here and 3 waters over there will cancel out in a second. Plus 3 H3ASO4. Okay, and we can cancel out anything that's left. So we have the iodine, or IO3. Is that an ion? Yes, ion. Minus charge there. Huh, wait a second. Oh, that's okay. I got lucky, right? I forgot the minus charge here and I forgot the minus charge there. So it's important to keep those minus charges because they indicate that they may make a difference in the charge balance. So if I had forgotten the minus charge here, then I didn't need to add 6 electrons. But fortunately, I've forgotten the minus charge on both of them, so the 6 electrons are still appropriate. So we should have the IO3 minus ion and the arsenic. Let's see, this is ASO3, arsenate, and arsenite. So this is the arsenite. So this is arsenous acid, and this is the arsenate. So this is arsenic acid. So the iodite ion, 3 arsenous acids, and yields iodide ion and 3 arsenic acids. Or arsenate goes to arsenic. Okay, so where are we at? That was number 37C, 3, 1, 1, 3. Okay, good. 637D, SO4, 2 minus, the sulfate, and the zinc ion. Zinc metal going to zinc ion. And the, SO2, sulfur dioxide. All right, so we have SO4, 2 minus, going to SO2. Now, again, it's important to carry our charges. I was kind of lazy that last time, but it's important to carry our charges because in the end, they're going to indicate how we have to balance our charges with electrons. Oxygen, sulfurs are balanced already, so we just need oxygen to the side that needs them with water, right? 4 H pluses now. Electrons to the more positive side. We have 4 plus, 2 minus. We have the need of 2 electrons over here. Okay. Now we have the zinc going to zinc plus 2. 2 electrons needed over there on the right side. All right, so we have our 2 half reactions, and there's 2 electrons in both. So that's nice. Just 4 H pluses plus SO4 2 minus plus the zinc metal yields the zinc, start up here, yields the SO2, 2 waters, and a zinc plus 2 ion. Anything the same on either side? Doesn't look like it. So 637D, zinc, sulfate, 4 protons, zinc ion, sulfur dioxide, and 2 waters. Excellent. 637E. Nitrate ion, zinc ion. Ammonia, zinc metal, zinc ion. So ammonia, NH3 plus zinc metal going to, what did it go to? Oh, no, not ammonia. NO3, nitrate, going to NH4 and zinc ion. And this NH4 has a plus. Again, very important to watch those charges. NO3 has a minus. All right, NO3 has a minus, zinc, NH ammonium ion, and the zinc ion. Okay, NO3 minus going to NH4 plus. This needs 3 waters over here to get the 3 oxygens. This needs 4 plus 6, 10 H pluses to get the correct number of protons. To balance this charge, we see this has a 10 plus, minus 1, a 9 plus over here, and then this has a 1 plus. So we need 8 negative charges. So now this has 10 plus, minus 9, it has a 1 plus charge. Sum on this side is a 1 plus, and this has a 1 plus charge on the right. So we have 8 electrons there. Okay, the other half, zinc going to zinc plus 2, and all we have to do left there is minus 2 electrons. But we're going to need 4 of this so that this matches 8 electrons over here. Electrons are going to cancel out. We're going to have 10 H pluses plus NO3 minus plus 4 zinc atoms, yielding NH4 plus 3 H2Os plus 4 zinc plus 2, and that's it. Okay, E, NO3, 4 zincs, 10 protons. Okay, looks good. F, chromium ion, BiO3. BiO4 would be a bismite ion. BiO3 minus, dichromate ion, and bismuth ion. CR3, BiO3 minus. CR2O7, dichromate ion, and bismuth ion. All right. Okay, so Cr plus 3 going to Cr2O72 minus. Okay, starting off here, we notice that the chromate is not balanced. So we need to balance the chromate before we balance our oxygen and our electrons, or our oxygen and our hydrogens. Before we balance our oxygens and our hydrogens, we need to balance our electrons. So I was looking for a better pen. There we go. Let's see if this one can work first for a while. Okay. So to do that, we need to have 2 chromiums here, right? 2 chromiums. That's done. Now we need to balance our oxygens, CrO7 there, Cr2O7. So we need to get 7 waters on this side. 7 waters over here, right? Now our oxygens are balanced, and now we need 14 hydrogens on this side, okay? Well, if we do that, we have to look at add electrons to the more positive side. 14 H pluses and 1, 2 minus, so that's a 12 plus on the left here. I'll write that down here so I don't have to redo it. Look again. 2, 3 pluses, that's a plus 6 over here. So to the more positive side over here, and I need 6 electrons. All right, because this was a plus 12 and that's a plus 6. I can double check always. Plus 6 over here. What's the net charge over here? Plus 14 minus 6, 8 minus 2 plus 6. Okay, so there we go. We have that one done. Bi, the other half, 3 minus, going to Bi plus 3. Bismuths are balanced. We need 3 waters over here, H2O, 3 of them, to get 3 hydrogens. 6 H pluses over here on the left. The more positive side looks like this side. It looks like it's a 5 plus, so it looks like we're going to need 2 electrons there. All right? So it looks like this one here needs to be multiplied by 3, so I'm going to change this to 6 so that the electrons will cancel out, right? 6 times 3, 12, 3 times 3, 9 waters. All right, 7 waters here, 9 waters on the left, so we're going to have 2 waters. So I'll cross out that and put a little 2 there. 12 hydrogens on the left, 14 hydrogens on the right. So we're going to have 2 protons on the right when we're done. 6 electrons on the left, 6 electrons on the right. So we have 2 chromium ions and 3 BiO3 minus. I don't know if the BiO3 minus is the bismate or the bismite, but it's an ion there. Probably the bismite. Product Cr2O7 2 minus, the dichromate ion. 3 bismuth ions, and then we have 2 waters left over on the left. Is that it? Did we forget anything? Our chromate, our chromium, our BiO3 minus, dichromate, 3 Bi plus 3s, and then 2 waters. Okay? That was 637 F. 2 chromates, 3 of those. Uh-oh. Oh, yeah. No. Wait. What happened there? We made a mistake somewhere. What did we do wrong? 3 chromates? Or no, 2 chromates, that's right. 3 of those, that's right. We have 4 H pluses on the left here. Why do we have 4 H pluses? And then we have dichromate, 3 bismuths, and 2 waters. So we started off with 14 H pluses here because we needed 7 waters. And was this 12 hydrogens right? Oh, that's the problem. That's not right. 9 times 2 is 18 here, so we needed 18 hydrogens here. And this is 14 here. Okay? So I miscalculated how many hydrogens we needed here. We actually needed 18, 14 there. So we're going to be left with 4 H pluses there. All right. Had to look in the back for that one. Okay. F. So now we're on to G. 637G. These are good problems. Lots of experience solving these problems. 637G. Iodine, hypochlorite, iodite ion, and chlorine ion. Iodine. I2OCl minus. IO3 minus. And chloride ion. All right. Let's start with the iodine. Okay. We need to have 2 here to balance that iodine. Now we have 6 oxygens. We need 6 waters over here. 6 protons. We need 12 H plus ions over here to the right. More positive side. This has 10 plus on the right side and no charge on the left side. So we need 10 electrons on the right side. Okay, OCl minus going to Cl minus, right? Water over here to balance the oxygen. 2 H pluses over here to balance the hydrogens. And now we're going to, this is the more positive side. It has a charge of +1, or no, 2, the 2 pluses and the 1 minus, +1, and we need 2 electrons to get to a -1. All right, so we add charges to the left, or to the more positive side to get the equal charges on both sides. All right, so now we have 10 electrons here, so we need to multiply this by 5, right? So I'm going to multiply this by 5 here, making this 10. Multiply this by 5, making it 10. 5 here, 5 here, and 5 here. All right? So now we can combine these together and see that the 10 electrons are going to cancel out. We have 10 protons over here, 12 protons over here, so we should have 2 protons left on this side. 6 waters, 5 waters, and just 1 water left over here. So we have the water plus the iodine plus 5 hypochlorite ions, yielding 2 IO3 minuses, 2 H pluses, and then 5 chloride ions. All right, that was letter G.